Now we'll see this problem. We have 64 registers and instruction set size is 12. That means there are 12 instructions and each instruction has 5 distinct fields. Okay, 1, 2, 3, 4, 5. So first one is opcode, second one is source register, third one is source register, then destination register followed by 12-bit immediate operand. That means I can fill this area with 12 bits. Now the remaining sizes we have to find out. What is the otherwise number of bits for opcode equal to dash? It depends on the size of the instruction set. Since you have only 12 instructions, to differentiate them, how many bits are required? 4 bits are required, correct? So I can say that with 4 bits I can generate 16 operations. Each operation corresponds to one instruction, right? So since we have only 12, then 4 bits are sufficient. 4 bits. Now source register. So register size, that means register identifier size depends on the number of registers. When you have 64 registers, 6 bits are sufficient to differentiate them. Then we can identify that register with 6 bits. Similarly here 6 bits. Destination register 6 bits. So finally 4 plus 6 10, 16, 22, 24, 34. Then finally instruction size becomes 34 bits. Remember it. Now in the problem they have mentioned that it is byte aligned. Byte aligned means when you have example, I will tell you with example. Let's say you have memory like this, main memory. Whenever the memory is byte aligned, that means you are using byte alignment, then what happens is your data is such a way that only some part of the byte is, let's say, filled. That means you have some 2 bits of data, okay, and you want to store. Though you have 2 bits of data, then we have to use entire byte because the next data we have to represent in the next byte. Then we say that that is byte alignment. Understand? So in this problem also this byte alignment is required. I will tell you why byte alignment is important in this problem. Now your program has 100 instructions. The amount of memory consumed by above operation is dash. Sorry, above program is dash. So here since you have 100 instructions, what is the each instruction size? 34 bits. Now try to keep one such instruction in memory. Let us try. You have this memory, right? Okay. So first 8, I assume that the machine is byte addressable. Of course in the problem that is given, byte addressable. So every byte is going to get what? One number. Okay. Of course that's a separate story. We don't really require here. So first of all, to store one instruction, how many bytes are required? Here you have 34 bits. 34 bits means what? 4 bytes plus 2 bits, correct? So first byte is occupied, second byte is occupied, okay, third byte is occupied, fourth byte is occupied. Now fifth byte, do you need entire fifth byte? No, only 2 bits. What about the 6 bits, sir? Can I use for another instruction? No. Here byte alignment comes into the picture. Whenever the model is byte aligned, then the next instruction should go to the another byte, not this used byte, I can say. So each instruction is now occupying 5 bytes, correct? Though the size of the instruction is 34 bits, effectively it is occupying 40 bits. Now we'll come to the problem. Program has 100 instructions. The amount of memory consumed by above program, very simple. Each instruction is effectively consuming 40 bits, then 40 into 100. So it is nothing but 4000 bits, correct? So either 4000 bits I can say, otherwise 500 bytes, both are same, right? So in that way easily we can solve the problems if you are strong enough in the foundations. Okay, now we'll see this question. In this question instructions are given, their sizes are given. What is the size of each instruction is, first instruction size is 2 words, second is 1 word, third one 1, fourth one 2, fifth one 1 word. Okay, so in the problem they have mentioned that word size is 32 bits. Okay, now one more thing they have given, it's a byte addressable system. Fine. Now the question is about if interrupt occurs when CPU has been halted after executing the halt instruction. That means when you are executing, that means after executing the halt instruction, interrupt came. Okay, now the question is about what is the written address? That means which address will be stored in the stack. We know one thing, right? Whenever interrupt comes, then the next instruction to be executed will be stored in stack, correct? So now we have to identify what is the next instruction, program counter has to point. We will see that. First of all, we will see really these instructions are stored in the memory. Where they will be, we will see. Let us number them. Instruction 1, instruction 2, instruction 3, instruction 4. And in the question they have clearly mentioned that the starting address of the program is 1000. That means program has been loaded from 1000 memory address. So this is, let's say, 1000. And instruction 1 is occupying, so 1000th byte followed by how many bytes? 2 words. Each word size 32 bits. 32 bits means 4 bytes. That means it is occupying 8 bytes, correct? So instruction 1 is occupying 8 bytes. They are 1000 to 1007, correct? Then the next instruction starts at 1008, I2. Since it is occupying only one word means 4 bytes, then the next address will be 1012. In that way, easily we can find out every instruction starting byte, correct? Or starting bytes address. I3 will be starting at 1012. So since this instruction, third instruction also occupying 1 byte, then I4 will start at 1016, right? Then I5. So I1, I2, I3, I4, I5. I5 is occupying 1 word. So that is going to occupy how many? Sorry, I4 is occupying 2 bytes, right? So here, because of that 2 bytes, then the next address will be 1016 plus 4 plus 4, 1024. So I5 will be occupying 1024 to, one word means 4 bytes, 1024, 1025, 1026, 1027. Now the next memory address is 1028, correct? Now the question is about whenever interrupt comes, then what is the, return address which is stored in the program, stack pointer, correct? It's quite easy to see here. So don't worry about this meaning, sir, how to execute this program. Don't execute the program, because already, in the program or in the problem, they clearly mentioned that you are executing halt instruction. Where is halt instruction? Here. And you have completed with halt instruction. After completing with halt instruction, then your program counter contains what? 1028. Agree? Because the next instruction starts at 1028, whatever it is. That is not mentioned in the problem. What is the next instruction? Okay. So your program counter goes to 1028 at that time, right? Now, at that time interrupt came. Now what we have to do then? We have to push this 1028 into stack, correct? So that once interrupt is completed, that means once interrupt service routine is executed, then we have to come back to normalcy, right? What is normality here? The normalcy is here coming to 1028, because up to instructions I5, which are located at, where last instruction is located at 1024, we have done with this, right? Now program counter was at 1028, then we have to come back to 1028. For that we have to store 1028 in the stack, correct? So this is a very simple question. So that's why I can say that option D is the answer, right? If you understand the question, nothing is there, right? See this question. A CPU has 24-bit instructions, okay? Now program starts at address 300. What is the legal program counter among A, B, C, D? Nothing is mentioned about byte addressability, everything. So what you can do is, to solve this problem, byte addressability is important, okay? We assume that, let's say, every byte is numbered, then only you get the right answer. So here I am assuming this system is byte addressable. If it is byte addressable, then how many, see, 24 bits means 3 bytes, correct? So that means each instruction is occupying 3 bytes. Really each instruction is occupying 3 bytes. Then what is the first instruction starts at 300, then it is going to consume 300, 301, 302. Then the next one will start at 303. The next one will start at 306, in that way. Now slowly you can understand that some of the numbers cannot be the starting addresses of the instructions, correct? So there cannot be an instruction at 301 or 302, because the first instruction at 300. Now you know one thing, whenever your program counter is at 300. If you increment it, 300 will become what? 303. That means it never becomes 300, 301 or 302, correct? So that's why always program counter points to the starting byte of the instruction. If that is the case, which number cannot come is the question. What we do is 300, 303, 306 relatively they are all, I can say they are moving, otherwise they are moving by 3 units, correct? To get a next number we have to add 3 units, 309, 312. So one surprising thing is, of course, that's quite obvious in mathematics, the difference between 300 and any of these numbers is divisible by 3, because every time you are incrementing by 3, correct? So that's why any new address, if you get in this model and the old address, starting address is 300, their difference is definitely divisible by 3, correct? So that's why you do one thing, you subtract 300 from everything, from the options. Okay, then what are you going to get here? 100, here you are going to get 200, here you are going to get 300, here you are going to get 400. Then only 300 is divisible by 3, that's why 600 is the valid program counter, but not 700 or 500 or 400. Just check it out, 300, 303, so on, you get 399, correct? After that directly we will jump to 402, correct? That's why, so here this 399 is, I mean the difference between 300 to 399, if you see that 99 is divisible by 3, correct? That's why I can say that to form any new address, the new, I can say new program counter value, that will be 300 plus some 3 into something. So that is the model of each instruction's addresses. That's why, so your this valid program counter also should be in the form of 300 plus some 3's, correct? So that's why 600 is nothing but 300 plus some 3's. How many 3's? 100 3's. That's why this is the only valid program counter. In that way, if you use some common sense, then easily we can solve the problems. Okay.